Okay, so this is a review for the physics test 2. So in this problem, we have Suhin throwing Kevin's ball into Malad's hole. So the height at which it's being thrown is 15 meters, and the distance away is 10 meters. And we have to find out what time does it reach Malad's hole, what angles can we throw it, and what apex, what's the apex, and what is the final velocities of each of the x and y. So first, let's find our v's. So that is going to equal, this is 41.0 meters per second. So v initial is 41.0 cosine theta, and then VO equals 41.0 sine theta. Then we can set up an equation to do the distance is final minus initial, so final is 10, initial is 0, so 10.0 equals 41.0 cosine theta times t. And then we can set up this one, and the final is 0, initial is 15 meters, so it's just going to be negative 15.0 equals 41.0 sine theta times t plus 1/2 negative 9.81 gravity t squared. Now, what do we do from here? We can isolate t to plug the t into here because t is relating to both of these projectile motions. So this is going to be 10.0 over 41.0 cosine theta equals t. Now, what can we do with this t? Just plug this into here. So let's expand this. Negative 15.0 equals 41.0 sine theta times, which is right here, time 10.0 over 41.0 cosine theta plus 1/2 negative 9.81 t squared. What is t? Oh, we have it. 10.0 over 41.0 cosine theta squared. Now, what do we do from here? We literally just do numeric solver, and I believe after doing that, we just pretty much get our thetas. And so our two theta answers are going to equal negative 54.7 degrees and 88.4 degrees. So those are our thetas. Now, what do these mean? So negative 54.7, so that would be meaning it's going down. It's going that way, 54.7 degrees. So that means the ball is going to be thrown like this, directly at Malad's hole. But this one, 88.4, this is almost perpendicular. This means 90 degrees. It's being thrown like really high, and it's going to come and fall back down into Malad's hole right here. Oh, yeah. And then, so that's that. And then what we can do is we can solve for the time. So how do we solve for the time? Well, we already set time, we isolated time. So we can just plug in these two thetas into this equation and get time. So when we're finding time for the one throwing directly at Malad's hole, we can do 10.0 over 41.0 cosine negative 54.7. And that is going to give us that. And then t equals 10.0 over 41.0 cosine, and then the other theta, 88.4. So now let's just think, which one do we think would take longer? The one that's throwing almost perpendicular and coming all the way back down, or the one throwing directly at Malad's hole? Well, the one that's going to be quicker is going to be thrown directly at his hole. So let's plug these numbers in. We get 10 over 41 cosine negative 54.7. We get 0.422 seconds. And then the other one is 10 over 41 cosine 88.4. And that becomes 8.74 seconds. So those are our two times. Now we need to solve for the final velocities. So how do we do that? Well, it goes Vf equals V naught plus AT, and Vf equals for x. Well, what is V naught? Well, we solved for it. It's 41 cosine theta, and we can use either, really. Let's just do the 88.4. So we got 41.0 cosine 88.4. We get 1.14, and then plus AT. Well, what is A for x direction? There is no A, so it's just 0, so this just cancels out. So this is the final x direction is velocity is 1.14 meters per second. Now we can do y. Vf equals V naught plus AT. So Vf equals, well, V naught is 41 sine 88.4, and that is 40.98, which comes out to 41.0, plus negative 9.81 times time. Well, what is time? Well, the time for 88.4, we solved for this, so 8.74. So now we just plug those numbers in. So negative 9.81 times 8.74, and then plus 41 to that. Our V final for y is negative 44.7 meters per second. And the last thing it asks for is the apex. So let's think about this. The apex is in a parabola, right? This is the apex, or the vertex. So if we're throwing it with negative 54.7 degrees, this is what that looks like. It looks like that. But for 88.4 degrees, it looks like more like a parabola. So this does not have an apex, so we don't even worry about the negative 54.7. But this one does have an apex, so we use the 88.4 degrees. So how do we do that? Well, we can use the Vf squared equals V naught squared plus 2as. And we have the apex, we're solving it for the y direction. What's the height going to be, pretty much? So Vf squared, well, at the apex, it's 0 meters per second is its velocity. So the final velocity is just 0 equals V naught squared. Well, we have V naught squared, which is, yes, we solved for it. It's 41 squared, which is that number right here, plus 2, A is negative 9.81, S, well, that's what we're solving for. It's y final minus initial. Initial is 15.0. And we can just do numeric solver here, and we get 100.67, or 100.7 for sig fix, equals 100.7 meters. And that is our y final, or the height at which this reaches. Okay, in this centripetal force problem, Ani is in Darsh's car, and Ani feels a force of 67.67 newtons going around this circle, and he weighs 67.67 kilograms, and his velocity is 6.7 meters per second. So this equation, we are tasked to find the radius of this circle he is driving in. So what is the equation? Well, the equation is AC equals V squared over R. So first, we have to find what AC is. So how do we do that? Well, AC, so F, we can use Newton's second law, F equals MA, and A is AC in this scenario. And so force equals MA, and what do we do? Just divide by M to get force over mass equals AC. And now we can just plug in our force and mass that Ani feels and is. So this is 67.67 newtons over his weight, 67.67, and that is going to equal, well, this is just 1, so AC is 1.000 meters per second squared, and we have to find the radius, and so we can plug in 1.000 equals v squared. Well, what is v squared? 6.7 squared over r. And what can we do? Algebraic rules, we can just flip these two to get r equals 6.7 squared over 1.000. And let's plug that in. 6.7 divided by, 6.7 squared divided by 1 is just r equals 44.9 meters. So r equals 44.9 meters. And that is how we do a centripetal force problem.